Okay, Bismillah ar-Rahman ar-Rahim. Salatu wassalam ala Muhammad Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Assalamu alaikum everyone. Last lecture, okay, not of the course, only of topic 4. Okay, so we still have one more topic. Today, inshallah, we're going to wrap up what we started 2 lectures ago on the stabilization control and SO3. Then we're going to quickly jump, okay, to how can we extend this to SE3. And then I'm going to show you finally some applications today, okay? So we're going to be, after we have this SE3, so going from SO3 to SE3, you've seen how easy it is usually because of the fact, everything geometrically, it's the same if you abstract stuff. SO3 and SE3 are 2 Lie groups, so they share a lot of stuff. Today we're going to be seeing this clearly. So this will not actually be a big jump. And going from SE3 to actually doing control of real drones, okay, is also not that strange, okay, given, okay, the abstraction of what we've done, okay. So today, inshallah, we're gonna, I think in my opinion, this is the most interesting lecture because you really see how you start from the theory and how all of the geometric, time, all the time was spent in the differential geometry pays off, and how this actually goes directly into something that controls the physical system. Okay, so recap. We started looking at these equations of motion. So the equations of motion that describe a rigid body rotating in its own place. So no translation. So R. So the state here is R, the rotation of the body, the orientation of the body. P is the angular momentum. The equation of motion given by this equation. The first one is simply R dot is equal to beta R as a function of omega. We said that beta R is the function that eats the omega as 3 numbers and gives you something that is R dot. Okay, so beta R is simply the equation that you all know, that multiplication by the left, okay, with R, okay, multiplied by the skew symmetric form of the omega. Okay, so this is what the beta R here is. And the second equation is simply conservation of momentum. You have the rate of change of momentum is equal to the gyroscopic torques and the control torques that you have here that we want to design a controller for. This is a system that's rotating in its place. So a natural energy function is simply just the kinetic energy. We don't have any potential energy function here. The tau, the control input, we design it as a summation of 2 terms, a proportional term and a derivative term. So essentially everything we've been doing is PD control. We want to stabilize the system at some desired orientation given by RD, and we want to have the velocity to be equal to 0. So this is our desired state that we want to go to. And we said the proportional term is derived given a potential function. So we're going to be deriving this as the gradient of some potential function, while the gradient here, or we need to properly generalize the gradient that in R3 or in Rn to SO3. And the derivative term, we derive it such that it will make the V dot negative definite, okay, if we can. Okay, if not, we'll see how we can fix this. This was the recipe. You start by defining an error function between R and R desired. We talked about that. What is the potential function that you are going to be choosing? We gave one option. You can have different ones. You can come up with something. You'll find a lot of alternatives in the literature. But continuing the recipe is the same. Okay, so you change the potential function, you're going to have different controllers, but the derivation is the same. So in order to derive the proportional term, we derived it first through the differential of the function that we chose. This is a covector in SO3, on tangent covector at the point R to this lives in the cotangent space at point R to the manifold SO3. And then we converted this differential to a proportional term using the concept of duality of linear maps, as we discussed last time. The only thing we did not do is what the derivative term looks like, okay? And usually we do this through the stability analysis. So today, inshallah, we're going to be doing the stability analysis and finalizing what the derivative term torque looks like. This is the error, okay? R desired transpose multiplied by R is the error between these 2 frames, the desired frame and the body fixed frame. This is the potential function we chose. It's half trace of identity minus R desired transpose R. Okay, so it's a function of R. You plug in R equal R desired. You find that the psi is equal to 0. And then we found that, as we've shown earlier, that this whole function actually can be written as 1 minus cosine theta for some theta. Theta is usually the angle between the 2 frames, okay, in some sense. So when we say theta is equal to 0, you actually mean R desired and R are the same frame, okay? And theta can be, the maximum value of theta is 180, right? And in that case, you know, you're as if you're rotating r desired and r are away by 180 degrees, okay? And away, this can be in many ways. I can, for example, I can rotate 180 degrees like that, 180 degrees like this, and 180 degrees like that, okay? So I have different alternatives. After that, we looked at the differential. The differential, by definition, is the covector that satisfies this equation. The left-hand side is specific for the manifold that we're talking, the vector space we're talking about. And we saw in this case, this is a 3 by 3 matrix, this is a 3 by 3 matrix. So these two terms, I just multiply them together and take the trace. This will give me the real number. And then this term, okay, was, okay, just how we compute the left-hand side. And by afterwards, this is the implicit definition. The term for the d psi of r, this is what we did last time. So we introduced this expression where this r epsilon is the curve, and then we differentiated that curve at epsilon equal to 0. We came up with that term, and then we compared these two terms, and we came to the conclusion that d psi of r is equal to minus half r d transpose. This is usually always how you do the implicit definition. Okay, just compare the right-hand side, the left-hand side, and whatever is left, this is what you have. Okay. And then we looked at, any question? Okay. Then we looked at how can we take this differential and convert it into a proportional torque. This was the, you know, the most complicated part. And we said that we use in this step, we use the concept of the duality of a linear map. And in general, if you have a map, the A that goes from vector space U to vector space V, then the dual of that map is another linear map called A star that goes from the dual of this space to the dual of that space. Okay, so they usually go opposite directions. If this goes from U to V, this goes from V star to U star. And it's defined again implicitly that if A star eats any arbitrary covector in V star, and then after that you get a covector in U star, and that U star eats any vector in U, this is equivalent to that A eats U first, gives you an element in V, and then the covector in V star eats that vector in V, and you get the same numbers in the end. Okay? And then when you apply that concept to the case of SO3, this is the map that we're interested in. So the covector we derived, so d psi of r lives here, and we would want to transform it back into a torque. Okay? So we want to write it as 3 numbers, okay, in the end. So the torque lives here. So the map that will relate this is beta r star. It's the dual of the linear map beta r, while the beta r is the map that would eat a vector, okay, 3 numbers, and give you the r dot. And this map, as we said earlier, is simply, if you give me any 3 numbers here, for example, let's say omega 1, omega 2, and omega 3, okay, I can put them in a vector, compute the skew-symmetric matrix, multiply that skew-symmetric matrix from the left by r, and I get this element. Okay? And this is how, if you give me the angular velocity itself of the body, and I apply the beta r, I get here r dot. Okay? But in general, this I can do it for any arbitrary, okay, vector here. And that's exactly what we did. So afterwards, we said that if this is d psi of r, we did a lot of derivations. Okay? The conclusion was we can define an error variable called er star that's given by the skew-symmetric term of r desired transpose r. Okay? Er tilde form, it means it's a skew-symmetric matrix. And r desired transpose r, as we discussed earlier, was not guaranteed to be skew-symmetric. That's why we do a skew-symmetrization of it. What is this skew-symmetrization? Simply given by this expression. The skew-symmetric term of any matrix A is A minus A transpose divided by 2. That's exactly what you see here. So this is the matrix. This is minus the matrix transpose. So this is the matrix, and this is its transpose. And then I take the difference, and then I divide by 2. And this is exactly what the error function, the error variable looks like. But this is in tilde form. How can I convert something in skew-symmetric form to 3 numbers? You just select, the 3 components. You've done it several times. And this is the S inverse. You remember what was the S? The S map is the map that takes from R3 to skew-symmetric. So what is S inverse? Takes a skew-symmetric and gives you 3 numbers. That's exactly the 3 numbers we're looking at, ER. And what is now the proportional control torque? Proportional control. Very easy. Now I have an error, and I multiply by some minus of some gain. I get the torque. Done. Yes, Fahd.
For the E tilde,
Yes.
is there another operation we could do to change it from a skew symmetric form into a normal matrix, or no? Other than the R D tilde or
This one.
Yeah.
This one.
Yeah.
From ER tilde to ER.
Yeah. No, other than doing the S inverse operation.
So you're asking about how can we convert a skew symmetric matrix to 3 numbers?
Okay,
Clear?
I get it. No.
Only one way.
How to do the R? Can we get RDTR without the skew symmetric form from the E tilde?
This term,
Yeah.
without doing skew symmetrization, it will not be valid.
Okay.
That's what we discussed last time, that R desired transpose R by itself is not skew symmetric. So I cannot equate it to something that's skew symmetric.
Okay. But we cannot change this into a non-skew symmetric form.
Which
We
one?
change the RD tilde R to a skew symmetric form.
That's right.
This equation.
That's right.
Can we do the inverse for the E tilde R?
This one. This is 3 numbers. No, you cannot.
Okay.
It's 3 numbers. So 3 numbers are equal to any 3 numbers. But the skew symmetric matrix must be equal to only a skew symmetric matrix.
So we cannot convert it from a 3 numbers to a skew symmetric?
From 3 numbers to skew symmetric, yes, you can. Give me any 3 numbers, and I'll convert it to skew symmetric form. But we're doing the inverse now. We want the 3 numbers. So this ER, sorry?
We want the skew symmetric to be 3 numbers.
That's what we did in this step. So the 3 numbers as the output, and the skew symmetric is the input, and the S inverse is just, you take the 3 numbers that are independent. So you have on the diagonal 0, 0, 0, and then you have x1 minus x1, x2 minus x2, x3 minus x3. So you select, I give you the matrix, you take the 3 ones that don't have the minus, and you say, I put them in a vector. It's a map. You remember we discussed this so many times. I know it's not like I multiply it by something. It's just you take the matrix, you select some input, some elements, and this you call it a map. And vice versa, the skew symmetrization itself is also very weird, right? I give you 3 numbers. You take this one, you multiply it by minus, you put it here. You multiply by positive 1, you put it here. And then you take the second number, you put it here with minus here. And you take the third one, you put it here and minus here. It's a map. And it's isomorphic between 2 vector spaces, but that's what you learned here. Right?
So, Doctor, is the skew, this SK,
Yes?
this is also an app or no?
The skew symmetrization is a map that goes, so this is an operation that goes from any matrix, so any n by n matrix, into the skew symmetric n by n matrices.
Okay, so does it have an inverse or no?
Yeah, that was my original question.
No, it doesn't have an inverse. And it's very easy because it's not isomorphic.
Yeah.
It's not isomorphic. Because here, this is actually a 9-dimensional space. For example, in our case, this is a 3 by 3 matrix. 3 by 3 matrices, so R3 times 3 is isomorphic to R9. So I have 9 dimensions. How many dimensions does a skew symmetric 3 by 3 matrix have? 3. So I took something that has 9 and I put it into something that has 3. So of course it doesn't have an inverse. Make sense?
Yes, yeah.
Okay. Make sense?
Yeah, it makes sense. Because I thought if we have a function, we should be able to invert it.
No.
A skew symmetric inverse.
You have a map and you have something called an invertible map.
Yeah.
Not necessarily. And that's a very good point because when we introduced the concept of a dual map, exactly what we're doing here, we did not require A to be invertible. We only required it to be a linear map between vector spaces, but not a linear isomorphism. It doesn't have to be invertible for this to work. That's exactly what you saw. Okay? And that's why the inverse of the map is different from the dual of the map, 2 different things. In case this is Rn and this is Rn, then A would be a matrix, A star would be the transpose of that matrix, and the inverse is something different from the transpose, as you usually know. So 2 different, 3. And not all matrices have an inverse, right? So that's the special case for Rn to Rn. Any more questions here? Yes, Ammar.
On a manifold, are all cotangent spaces the same?
No.
Well, go to the arrow. Hello? Yeah. Can we say that now the arrow is a cotangent at the point, at the moment, and the torque
That's right.
is also a cotangent at the point?
No. The torque, so this one
You defined it this
is related to ER. and ER are three numbers. It's a covector. And it's isomorphic to the Lie algebra. So actually the torque lives here. Lives in the dual of that space. What is that space? That the tangent to the identity.
So this is what's it called?
Lie algebra.
Lie algebra.
The dual of the Lie algebra.
Yeah. The dual of the Lie algebra.
So your question is not correct because you started by saying a manifold. This is a controller, we can only do it in a Lie group.
Lie group.
This is only valid for Lie groups.
But
To generalize that controller for manifolds is a little bit
implicitly
involved.
we are doing all of this stuff on Lie groups.
So far, this controller is only on a Lie group.
Even the E is on Lie group, and the tau should be also on a Lie group.
No, the tau
Tau tilde.
The tau tilde exactly
Tau tilde.
is in the Lie algebra of the Lie group. That's correct.
So I'm asking, are they on? Can we say that any two what's it called cotangent spaces are related to each other with just a constant?
On a Lie group, only on a Lie group.
On a Lie group.
On a Lie group, you always have an isomorphism between any space here and the algebra. So the tangent space here, I can always go back and forth, okay, to the algebra. And the dual is also the same. And that's exactly the figure that you see here. So I can always, and actually we introduced this map one time before. We called it the push forward of the left translation map. Go back and find it a long time ago we discussed. And that's its dual.
Yeah.
And this is the S, and this is the, it should be the dual of the S, but it's the same. It actually does the same thing. And this is actually the beta R. So to read this, actually, you know how it works. So this is the beta. I first converted to beta, this is the omega. I first converted to omega tilde. Then I take the omega tilde, multiply it from the left by R, I get R dot. And taking the omega going to R dot is simply the beta R. And what we did last time implicitly was actually taking the d psi of R and converting it to the ER tilde, and then taking the ER tilde, converting it to the ER. Okay, that's what we did last time.
Yeah. The thing that I'm exactly asking about is we reached R3, the tangent space of R3, right?
That's right.
Then we assumed that this tangent space, this cotangent space, is related to the torque with some proportional term.
That's right.
Is that always the case? Or?
For the controller we derived.
Okay.
Yes. For doing it on SO3, that's usually the way, yes.
Okay.
If you start by some potential function here, by the differential of the potential function. This is, you can always do that.
There are more, there is, it's not this one case, there are cases.
Cases of?
Other stuff. It's not, for example, these two cotangent spaces are not related.
So the thing on, so that's a good, it's a question, but I think it will take a lot of time for you actually to really digest it, but I'll just give you in a nutshell. The best thing about Lie groups is that the fact actually that they have this algebra. And usually when if you want to do something on the Lie group, you always go back and forth to the algebra. You go to the algebra, do stuff there and come back. This is how we did the control, okay? So we started by saying I have a potential function on the group, but then afterwards we converted everything to the algebra, okay? This is how you do estimation on the Lie groups. This is how you do, for example, Kalman filter on the Lie group. You always take, if I'm gonna do stuff here, I send it back to the algebra, do the computations there because it's a vector space and it's not changing, and I come back. So you always go back and forth to the algebra, okay? And you can do it, and you can generalize it to more different settings. This is special for a Lie group. General manifolds don't have that nice structure, and that's what we said earlier, that Lie groups, they have a more structure than a manifold. A Lie group is a manifold and a group, and this simplifies some stuff. Last step, okay, so this is our closed loop system now. So we have R dot is equal to beta R of omega, and we have P dot is equal to the gyroscopic term. We have the proportional derivative term. We said that the proportional term in the end is simply minus Kp multiplied by beta R star. So that's a function of R. And it eats d psi of R, which is another function of R in general, okay? So now you see, if you look at this step, this is a x dot equal to f of x. Of course, this is a very nasty f of x, okay? If you look at beta R star of this term, this is actually all of that stuff. So it's R desired transpose minus R transpose R desired, and I take the S inverse. Okay? It's still a function of R, but it's not that nice. Okay? Now, Lyapunov analysis. Okay? Lyapunov function. Okay? the original kinetic one that we had plus the potential one that we added. Okay, I'm going to multiply here this by Kp so that stuff cancel out. Okay, and by the way, alternatively to what we do here, we could have included the Kp inside of the definition of the psi itself. I could have written this as half Kp transpose I minus R desired trans R. Okay, and then we could have not written it there. Okay, so you can do it this way or that way. It's just a constant. So this is our Lyapunov function. This is the dH of P, it's simply given by omega transpose, and d psi of R is given by minus half RD transpose as we saw earlier. So after we compute the V, and we have the differential of its two parts, this is a function in general of R and P, but it's differentiated into, it's distinguished into two parts. One which is only a function of P, and one which is only a function of R. Okay, so this actually will simplify stuff when we calculate the V dot. So V dot is equal to H dot plus Kp psi dot. Make sense? H dot is the dH of P multiplied by P dot. Okay, and but this multiplication is actually a duality because this is a covector, this is a vector, this is R3. D psi of R and R dot live in that space, so it's a duality on that space. Is that clear for everyone? Afterwards, we're gonna take that term, we're gonna play around with it, and we're gonna leave this one for a while. Okay, so only focus on here. So R dot is equal to beta R as a function of omega. You all agree? Everyone? Yes. R dot is beta R of omega from the dynamics. Okay? This expression, I can evaluate it by the duality. We said that if I have something that eats a vector, okay, I can also rewrite it as something like this. I can convert it to I can take the beta R to the other side, of course the dual one, and the vector space also changes. Make sense? And this whole term beta R star d psi of R is actually nothing else than 8R. Is it clear for everyone how we went from here to here? If not, we repeat it. We all have to be on the same page. Yes or no? Clear? So that's where we're at right now. How can we move on further? Let's continue with the dynamics. We still have P dot, and P dot comes from the dynamics. So we can take the P dot and just substitute stuff here. So the dH of P is given by omega transpose, and P dot is given by this expression. And here we have omega, so KPER multiplied by omega, which is equivalent to omega transpose KPER. And then just expand that stuff, okay? And we have this expression. Make sense?
The omega transpose KBR.
Where did it come from? So what is this term? How do you read that? This is the duality product of a covector and a vector in the vector space R3. If I give you this covector and this vector, okay, I can write it as KPER transpose multiplied by R. ER here is written as 3 numbers, right? So it's a column vector. And this is another column vector. So how can you take the duality product? I transpose one multiplied by the other. And this gives me a scalar. So I can transpose the first multiplied by the second, or transpose the second multiplied by the first. That's exactly what we did here. I just chose to transpose the second multiplied by the first. Yes?
P minus?
Where?
Minus omega t, kp.
Here.
Yeah.
Go back to the derivation here. This is d psi of R. This is beta R of d psi of R.
Because of the transpose.
No.
For the cross product.
Cross product, yeah, exactly. Cross product has that.
Okay.
If I clear? Okay. So this is where we are right now. How can we simplify this? The term in the middle, what happens to it? What happens to the term in the middle?
Goes to 0.
0. Kp minus Kp, you get 0. No matter what you multiply, it's 0. This term, what happens to it? How can we simplify this term?
Is it symmetric, right?
What happens to that term?
6 numbers.
We can do it as minus omega transpose omega
We
tilde
can,
and p.
take your time and take pages.
We can
This is what you do usually if you write stuff in coordinates and you play around with. What is this equal to?
d delta omega equal minus omega delta.
Play around as you wish. Yeah? There's much easier way. Yeah, exactly. And write it down and substitute omega to be omega 1 and omega 2.
You can take omega transpose out.
It's already out.
Also with TD.
No, forget about that stuff. Just look at this term alone. What happens to that term alone?
Joint of the
0.
yeah.
We said a skew-symmetric matrix.
Yeah.
If I multiply it from the left and the right by the same vector in this expression, okay, it's always 0. That's the definition of a skew-symmetric matrix. Okay, it's a property. It's always like that. Any skew-symmetric matrix multiplied by anything on the left and the right, it goes to 0. If you don't write stuff in this way and you do it in the standard way, if you took any course on nonlinear stuff and you start writing things with components, you start to have, I cancel this one with that one, and this one with that one, this one with that one. It's actually in one line here. Okay.
Again,
Skew-symmetric matrices,
that b.
the P itself.
Okay.
I took the P, it's 3 numbers, and this is P tilde, so it's a skew-symmetric matrix, and I multiply from the right and the left by some vector, by the same vector, so it's 0.
Any vector, the same. One.
Any skew-symmetric matrix and any vector will always give me 0. So in general, X transpose A multiplied by X for any X and for any A that's skew-symmetric is always 0. 0, 0, I'm only left with that term. Okay. Another thing, you remember how ugly our proportional controller looked like? The ER, do I need to remind you?
Half and
No. All of that stuff, right? Did I plug it in? Did I plug all of that stuff in, or did I plug it implicitly by this expression? And by implicitly by this expression, it already cancels out, okay, with the other term. Go here. So here implicitly we got this term, and also the P dot has the controller which is minus of that term, and they just cancel out. Okay? And that's actually by the way the reason why we multiply by Kp here, so that we can easily cancel them out. Okay? That's something for you to try at home. If you don't multiply here by Kp, you don't get this Kp here. So you have Kp minus 1. Okay? Whenever you're stuck like this, very easy. Just go back and try to change the Lyapunov function. That's exactly what we did here. Okay? So that's for you to look at home. This is where we're at. How can we choose the controller, the derivative controller? Very easy. I know that I need to make this negative definite, so I multiply it by something that has minus kd omega. So a linear, just a derivative controller. By the way, I'm not, if you want to make it really fancy, you're not bound actually to make it linear. It's the easiest choice to make it just that actually tau d is equal to minus kd omega, but I can make it any nonlinear function of omega, and it will still work. Okay? And tell you even something better. I can even make it something that's time-varying function of omega, and still this will be the same. Okay? So I can make the derivative term here a time-varying function. So in case you have an application that you want, for example, kd to be time-varying, this is usually what people do, for example, in haptics. You want actually the damping to change with time. Nothing in the Lyapunov analysis will change. Because it's still negative definite. Of course, it's not negative definite, unfortunately. It's what? Why? Why is it only negative semi-definite? I started from V, calculated V dot. I found something that's less than 0.
Because it's only related to the R, not to the
Exactly. Because here it's only a function of omega, and the OR can take any value. And we said that this can only work, okay? It's negative definite if I also have some negative definite function of R as well. It has to be of R and omega as well. Okay? So what do we do? Lassalle's invariance principle. Okay. So take the omega to be the whole state space. So the set R, okay, is the set where V dot is equal to 0. That actually should be here, a typo here. So this should be V dot equal to 0. So this is V dot is equal to that term. If V dot is equal to 0, what is the set R, what does it contain? It contains all of the rotation matrices and P that have the value 0. Because if V dot is equal to 0, and we chose KD to be a positive definite matrix, sorry, this actually should be minus KD, okay? But it doesn't matter because we want it to be equal to 0. So KD, we chose it to be something that's always positive, which means that this expression is 0 when omega is equal to 0. And if omega is 0, this already implies that P is 0, because omega and P are just multiplied by the J, the inertia. Okay? So omega 0 is equal to P is equal to 0. So this is the set R. It consists of all rotation matrices and all P's that have the value P equal to 0.
Okay.
This is the R. What should we find inside of the R, remember? The largest invariant set. Okay? It's the set that not only has P equal to 0, but also has P dot equal to 0. Okay? I should start there and I should never leave it. So P dot is equal to that expression from the dynamics. And if this is equal to 0, but at the same time, remember that M is inside of R. And R has all of the P's equal to 0 and all of the omegas. So this term should go to 0 and this term should go to 0. So we're only left with the set, okay? We're only left inside of M with all of the points that satisfy the ER equal to 0. ER itself, ER was something we know. It's not the skew symmetric, but the ER tilde is the skew symmetric version of it, and it's equal to that term, and this should be equal to 0. Which means that it's R desired transpose, R minus R desired, R transpose RD, divided by 2, multiply both sides by 2, nothing will change. So I'm left only that RE is equal to RE transpose. This is the condition. RE should be symmetric. That's a symmetric condition. Okay? So conclusion, we have that the largest invariant set is the set of all points R and P that are inside of omega or inside of R that satisfy P is equal to 0 and R desired transpose R is equal to R RD transpose. Okay? Now the question is, how many R's satisfy this? How many rotation matrices satisfy this condition? Let's see how much time we have. Okay. Let's start with the R that we adore the most. What is the R that we adore the most here for this controller? R. Which R you love the most? That you really want to study as stability? R equal? R equal? R desired. The R, you're talking about RE. RE is the identity, yes? And RE is the identity if RD is equal to R, or R is equal to R desired. Make sense? So in case I substitute here R to be R desired, does it satisfy this equation, this one?
Yes. Identity is symmetric.
So this is R desired transpose. Multiply by R desired. What do you get? Identity. And is the identity equal to R desired multiplied by R desired transpose, which is also identity? Yeah. In other words, to actually ask it in another way, is the identity symmetric?
Yes.
Of course. 1, 0, 1, 1, 1, and everything is zeros. You symmetrize it. You transpose it. You get the same matrix. So alhamdulillah. The point we want is included in M. Is it the only one? Remember how we do Lassalle's variance principle? It should be the only equilibrium point there so that we can conclude it's asymptotically stable. Is it the only equilibrium point? Okay. No, it's not. Okay. It includes, there are at least 3 more points. The most interesting one are actually 3 more. So there are the three matrices that you can make with 180 degrees rotation around, okay, the 3 axes that you have. So identity is this matrix. So if R equal R desired, is that the error is 0. Right? The error is 0. It means they know both are, the relative orientation between them is identity. So they both have the same. Okay? So this is identity, the error. If I rotate around 180 degrees, okay, in this direction, that's one matrix. That's also symmetric. If I rotate around this axis by 180 degrees, I also get a symmetric matrix. If I rotate by 180 degrees around the third axis, I also get something that's symmetric. And that's left for you as a homework to try out. Okay? You have the Rodriguez formula. Go back to the Rodriguez formula and just substitute pi, the angle equal to 180. And choose once the x axis, y axis, and z axis. You're going to get 3 rotation matrices. You're going to find that they are invertible. Sorry, they are symmetric.
That's applicable only on the when I rotate 100 degrees about the basis.
180 degrees, yes. If I rotate around any other axis, that's a good question. I haven't thought about it. Okay, but these are at least the 3 I know of.
If about any axis, so it's infinity.
Exactly, you have infinite number of points. Absolutely, yeah. And I guess this is also the case. Okay. So now 2 things. First of all, it's left for you. So this you're going to be implementing this in the assignment, inshallah. Okay, so there will be a new assignment, okay, posted this week. It will be designing a stabilization controller for SO3. So implementing this, and then taking the simulation and playing around with it. Start the initial condition, okay, with 180 degrees, of this rotation I just made, and check what will happen to the controller. You'll find that the controller is not moving, because it's actually an equilibrium point. Okay, so the points. If M has these R's, this means that if I start at these R's, I should stay there. Okay, so these are almost like singularities with respect to the controller itself. Okay? The controller breaks at these points. Okay, so that's the first thing. Now there is something we can do here, okay, about it. But we'll need to go back really a lot. Okay?
Doctor, I'm sorry, but
Yes?
180 degrees or 360?
No, 180. 360, then you go back to the identity.
Yeah.
If I take the identity matrix, I rotate 360 degrees, it's identity. So that's okay. Make sense? And also the 360 degrees not included. Remember?
It's from negative pi to
It's from minus pi, even minus pi is not included, and to pi. Okay? Now the way, I'm not going to, so you have 2 options now. We can either, I can take you to the board, we can do this in math to really show you what will happen, in this situation, or we leave this and go to drones. What do you decide? So analytical stuff or practical stuff?
We can go practical.
Let's take a vote. Who wants to see the analysis? Who wants to go to the drones? Okay, so drones it is. Okay, that's what I expect. Okay, the stuff is there, so I'll give it to you to read. You'll find it here and there in the literature. Okay, so but that's the bottom line. Okay, that in the end we have actually 4 equilibrium points in there. To fix it, actually, we're going to do the same trick that we did with the pendulum. You remember what we did here in the omega? We started from the whole state space. What we can do here is that we can start in the region that excludes the other equilibrium point. And that actually, the other equilibrium points, they have theta equal to 180 and psi equal to 2. Remember the psi was from 0 to 2? The psi of R was from 0 to 2?
Yeah.
So what we're going to be doing is that we're going to be excluding the 2, and by doing that we exclude the other equilibrium points, and then you have local asymptotically stable. Bottom line, this controller, with more actual analysis, you can show that the other equilibrium points are unstable, and the bottom line is that this controller is globally asymptotically stable, between brackets, almost. It's almost globally asymptotically stable. How is that important for drones? That's exactly what we're going to be seeing in the next part. Okay. First, before going to drones, you cannot implement this controller directly. This controller that we just derived, that has, to go back now, so that has the proportional term equal to minus kp er, and the derivative term equal to minus kd omega. You can implement this on something that has only rotations, and the typical thing is actually a satellite. Okay? So a physical satellite, you can do like this. Or if you have a drone and it's fixed to a base, for example, like a gimbal, and it's not allowed to fly, you can also apply this controller. But if you have something that's flying, you still need to go from SO3 to SE3. How hard is it? Okay. That's exactly the recipe to go on SE3. So we need an error function between H and H desired. We need to design psi of H so that it's positive definite, compute the co-differential, convert the co-differential now to a proportional range, so we should get 6 numbers here, not 3. And we should calculate the derivative range in exactly the same way. So first term, this is the error function. Make sense? Not transpose anymore, but the inverse. Okay? HE goes to identity as H goes to HD. Make sense? Okay? Now the 2 frames, the 3 frames are not at the same point. They're allowed to move around. So the psi desired can go around. Psi B is fixed to the drone or to the body, and psi S is the inertial frame. The function that you can choose, you can be as innovative as you wish. There are no limits here. The easiest thing that you'll find people doing, and they make their life easy, is simply say that I have a function of H, I'm going to split it into 2 parts. One in translation that only focuses on the psi, and another one that focuses on the R. The one that focuses on the psi is given by this expression. Have you seen this one before?
Yeah, the potential energy.
It's exactly the potential energy function that we used for the point mass, right? And this is exactly the same expression we have for SO3, except for one small detail that we have here G0 exactly. So remember someone asked last time about that actually the controller we implemented treats the X and Y and Z errors in the same way, because I just multiply it by a KP scalar. That's the controller we designed. But here with this expression, actually I can make this into a matrix. So actually G0 here actually is like a stiffness matrix. So I can make it, I can couple the X with the Y or make the X faster or the Y faster and the Z faster and so on. Okay?
How is that useful?
In case so for a drone, usually it depends on how the distribution, of course, in general of the motors. But usually you might have a configuration that produces more torque in this direction than this direction. So it's more powerful this way. So you don't need to put a lot of control effort in this way. So you need actually the gain to be very small here, but the gain to be very high here. That's right.
So the G here, it is a matrix, gain.
It's a 3 by 3 matrix, yes.
Gains, right?
It's gains.
So can, for example, mix between some terms.
That's right. And you can even couple. So for example, I can have an error in the X give me some torque in the Y if you want, in general. It just needs to be positive definite.
So how can we design this?
It's a gain, controller gain, just like the KT. It's a gain.
Okay. So
You tune it. KP, you play around with the gains until you get the desired performance.
diagonal, I think it will be easy.
The G0 is not diagonal. Okay, the G0 usually is called a co-stiffness matrix, and it's related to the KO. You can define a KO that you can make diagonal, and the GO will be a little bit different. And I'll point you some reference if you want to read about it. Okay, this is how if you want to modify the one that goes inside. Okay, yes, no man, no question. Any more questions?
I guess this G can be diagonal, can be skew symmetric.
Not definitely not skew symmetric. It has to be definitely symmetric. G has to be symmetric such that this whole function can be positive definite. They are definitely related. Okay.
But I think it should, in the end, it should be mapped or isomorphic to R3. To be just 3 numbers.
No, the gains, they don't have to be R3. So for even take the KTs for simplicity. The KT, you always choose it to be diagonal, right? Say KX, KY, and KZ. But nothing is wrong against making actually cross-coupling terms. But they should be symmetric. Otherwise, you don't get this to be a positive definite function.
Should it be symmetric in order to multiply it by the I minus RD transpose?
This one you mean?
Yeah.
That's a very good point. Yeah, okay, so that's an excellent point. So what Muhammad is saying is that this term will appear, actually, let me go back, will appear here. The proportional term here. So you see here when we add this, if you start from the psi including the G, and you compute the error will have G here and minus G here. So actually you can show in the end that we have the skew symmetric term. So the ER tilde is equal to the skew symmetric form of G0 multiplied by R desired transpose R. And thus, it doesn't matter whether it doesn't need to be skew symmetric, okay? Because you're going to also skew symmetrize it in this way. So that's exactly how it will change. You're going to have the G here. But it should be positive definite on its own, so that when you go back to this step, when you check whether the psi you chose is positive definite, you'll find that this raises a condition on the G that it has to be symmetric, positive definite. And if it's positive definite, it has to be symmetric. So symmetric and positive definite are always there, side by side. Okay? So let's fast forward again. So this is the psi that, okay, so this is the psi of h that you find easiest thing to work with. I split the translation and the rotation, there is no coupling. Now, is there anything that prevents us from coupling rotations and translations? Of course not. And then you have so many ways that you can play around with. So I give you this reference. This is an excellent paper. It's a classic one, okay, by the authors of the book that, the big yellow book that it's already on Blackboard. I'm pretty sure no one looked at it, okay. But in case you're curious, this is the geometric control book by Bullo and Murray. And this paper, they did tracking control for fully actuated, okay, mechanical systems. Yes, Fahd.
Why is it useful to couple these stuff? I thought that coupling, if we intentionally couple them, wouldn't we make it more difficult system?
It's more complicated. Yeah, exactly. The derivation that we did is exactly the same. The Lyapunov analysis is exactly the same because you remember we never plugged in the psi, we just left it abstractly. So actually the derivation is very simple. It's the same for all of these. It depends on the application. What they did in this paper is that they started proposing different stuff. One out of all of these actually, this I like actually the most, okay, this function here, okay? And the reason is that it has very nice properties. It has actually something, it's a symmetric property. The function itself is symmetric, and it also has invariance, okay? And this is a big topic, okay, that no time to look at, okay? But this actually, okay, function, I used it, okay, to design a controller. I'll show you the implementation in a bit, okay? But in principle, what I'm trying to say here is that you have many options for, okay, the psi. And you see all of these. This is the one that we have here, actually. That's exactly the one. The first one is the one that is written on top. Just need to translate it. And the rest, they all have coupling between the R and the P in some way.
So
Okay.
you couple the KB for all the angles?
No, they coupled the rotation part and the translation part. Essentially, what this does is the following. If you take this controller, okay, this controller, we're going to be deriving from it a wrench, right? So 3 torques and 3 forces. The force part will be related to the error in the position. And the torque part will be related to error in the rotation. If you couple them, then an error in the force will give me a torque. And an error in the rotation will give me a force. Okay?
Which is actually more related to the mechanical, fully actuated mechanical.
It depends on what you want. Exactly. It depends on the application. The reason I'm talking about this one is that there is a certain application where actually this one has been shown to be superior. And I'll come back to that later. That's impedance control. But I'll come back to that later. Okay, in 2 weeks, inshallah. Okay? So, yes, stop.
The first one, it's not invariant, which is the same that we're using.
That's right.
But what does it mean not invariant? Invariant to what?
Big story. This lecture will give you more questions than answers. I'll just opening all of the doors, and I'll leave you on your own. If you want to swim, you swim. Okay? My role is done here. Okay?
It's sort of like a trailer for another course you are going to.
No. If you want to do research, you can. It's on your own. This is for your own learning now. Okay? So how do we convert this code? So step number 3 is that after you choose the function, you compute the codifferential. But you saw, okay, this is just some math that you need to go through. And after you get this codifferential, the big question is, how do you convert this to a wrench? All right, a proportional wrench. The proportional wrench will be equal to beta star d psi of h. Okay, what is this beta star? It is the dual of this map. What is this map? It's the map that takes 6 numbers and gives you h dot. It is the map that you give me a vector, I put it into skew symmetric form, and multiply it from the rest by h. You've seen this so many times. It is the h v tilde and gives you the h dot. Same idea. Okay? And how do I make this? I just put the left-hand side, the right-hand side, and I try to play around until I get the wrench. Okay? That's it. Okay? That's SE3. Done. Okay? How do we make this into real life? Okay? So MAVs, okay, is short for multi-rotor aerial vehicles. Okay? It is the most popular choice, okay, simply because you don't need to know any aerodynamics. That's, my opinion, the only reason why it's very famous. Okay? Aerodynamics is very hard, okay? At least for people that are in robotics. Okay? It's a lot of mechanics, very hard. Okay? But if you just have propellers, you don't need to know aerodynamics. You just rotate the thing, it gives you a force and a torque, and that's it. So any bachelor student can understand that. When we have this drone, okay, this MAV, and we have all of these rotating propellers, we never think of it as actually a multi-body system. We always think about it that it's just one rigid body floating, and all of the propellers, their inertia is just negligible. In practice, this is also it's a valid assumption because the inertia of all of these propellers is usually very small compared to the whole drone. Okay, so usually we just neglect the inertia of this rotating propellers. So in the end, it's just the propellers are just the control to our system, and we just consider it as one rigid body. So if you want to control a drone, it's equivalent to controlling one rigid body. What's the configuration space of one rigid body?
6.
What's the configuration space called?
SE3.
SE3. So I want to control the drone, I do control in SE3. Okay. After you design the controller that we saw, so the controller term here for the rigid body, which should be, for example, in the what we've done so far, it's PD. It's like proportional wrench plus a derivative wrench. The proportional wrench is minus the differential of the psi function I chose converted to the 6 numbers, and the derivative term will be minus KD multiplied by the twist. So this will be the PD controller there, similar to what we did. Okay, and then afterwards I need to convert it into individual rotor thrust, and I'll come back to that. Yes, Fahd.
Going back to the idea of SE3, so there are other vehicles that we cannot use SE3 for, aerial vehicles, for example.
Aerial vehicles that it's not enough to say it's SE3
Yeah.
as the configuration.
Yeah.
If you have very big propellers, or in other words, if you have that the inertia of the propellers or the angular momentum of the propellers as it's rotating is not negligible, then you cannot say that, okay, I can, it's just one rigid body.
Okay, it doesn't have to do with the type of thing we're flying.
No, it's just the scale. At this scale of drones, the drones that you can just hug, all of these drones, they're huggable, okay, as big as that, okay. They are actually the propellers we use are very small, okay, inertia-wise, okay, and that's and at the level of if you just compare both, it's not worth actually that I take their inertia into account. You can always think of them as disturbance that the controller will take off, but not really model it as something that I need to take it into account. Yes, Asha.
Is there some sort of comparative percentage for the inertia of the propeller that it should be?
It's a modeling assumption. No,
No,
you want to.
I'm saying because you said when it becomes large
Yeah.
enough that we cannot ignore it.
That's right.
If the propeller is large enough, then surely the body has to be large enough as well.
Absolutely.
So then there has to be some comparative term that we can say if the propeller is this much smaller.
Absolutely.
then
I have no idea. I have no idea about the numbers. It's just an intuition. And exactly the same. If the propellers themselves they become big, also they take into account. Okay, that fact. That's also one thing. Another thing that usually people do is that if the propeller is fixed, usually the gyroscopic effects that come from the inertia are not that significant. They become significant if you start to rotate the propellers around actively. And this is actually, for example, all of the drones you see on the down here. All of the 3 drones that you see here, they are actually actively tilted. They have propellers, they have motors that tilt the rotating propeller.
So not SE3.
In that case, it's still one rigid body, but it has now, it's actually, properly speaking, it's actually a floating base. It's a floating manipulator. It's a floating base manipulator. Because you have all of these 1 degree freedoms, as if they are like joints. They are actually joints, but as if you have, multiple arms there. Okay.
So how do we calculate the KB and KD?
KP and KD, these are gains. You tune them. You have so many options depending on the performance you want. You want it to be very aggressive, you want to be very soft. It's up to you.
In the normal control, we had to calculate the KB and KD,
Such that the system is stable, right? We have the conditions here. We said that KP should be positive definite, KD should be positive definite. That's the only thing for stability. Anything else is possible.
trial and error and manually.
It's trial and error and manual, yeah.
Sometimes implement neural networks and some other techniques.
Go crazy and go reinforcement learning and as you wish. Tune the gains as you. Tuning the gains is not part of the problem. What we're doing here is only designing the controller and making sure it's stable. Performance is a completely different story. You're talking about performance now. How do I choose the gain such that it's well performance? But performance is related to the criteria that you judge it on.
If we have in our project we have 3 KB and 3 KD. So,
Yeah. In the controller, in the function I selected for it has 24 parameters.
so if we want to do a trial and error, it will take a lot of time.
That's an excellent point. And this is where simulation can help you. Build the simulation, leave it running, take all of the stuff that you did, then compare together. That's actually what reinforcement learning does, right? Just runs the simulation again and again and again, and then just optimizes and tells you, okay, this is the best thing, roughly speaking, right?
Doctor,
Yes.
if we choose one of the MABs in the pictures below,
Yeah.
so it's actively rotating or tilting the
Yeah.
propeller. So we can say that it's locally or partially, we can model it as SE3. In the transition phases, it's not SE3.
It's all the time changing. That's the thing. It's all the time. This is one of the degrees of freedom that the controller has. It's all the time the propellers are doing like this. So it's not like that, it's not like what people call a VTOL. It's not a vertical takeoff and landing. That, you go up and then you switch 90 degrees and then you start flying. That's not the case. The angles here are always changing. Okay. One way to do it, but I'll not go there, okay? But it's up for you to investigate, as I said, okay? Now, the way that actually we convert the control wrench that we computed with the PD controller to the individual rotor thrusts is actually called the control allocation problem. The control allocation matrix itself, computing it is not that hard. If you had the fully activated drone, you should have been able to do it. From the URDF that you have, finding them is not actually that hard. It's very easy to compute. Okay? And afterwards, taking this, converting to that, becomes just a control allocation problem. For those who have the fully activated drone, this is simply inverting a 6x6 matrix. That's not depending on time, so it's actually invertible matrix. So that's actually the main reason why I told you to choose the fully activated hexarotor, because the control allocation problem is very easy. If not, it becomes a problem by itself. Okay?
But that's variant to the orientation, to the default orientation of the URDF, of the base link, for example.
What sense?
So if I spawn the hexarotor with a 0, 0, 0, or
No, this is all in the body frame. Only the body frame. It doesn't matter where you are. Okay? So you convert. So for example, I have one propeller pointing upward here, one propeller pointing upward here. So I have a force up, force up. How do these, for example, correspond to the torque there? So you just have this one minus that one, or this one plus that one with some length. So that's exactly what's in the control allocation matrix. So what I want to show you now is this is the SE3 controller, okay, implemented. Okay, so let me show you the videos. So that's the drone. Okay, we have it down in the lab. Okay, I'll leave you some noise. Okay. You see here, this is the desired frame, and the controller just takes the desired frame, tries to go to it. Okay. This drone is fully activated. Okay, and it's fully activated means that it's moving without rotating. It's unlike the quad rotor, right? That's actually a fully activated hexarotor. Okay, so you see here at its own place, we change the desired frame, the desired orientation, it just goes to it. Okay, and this is the PD control that you saw right away, just symmetric. Okay, this the geometric one. Okay, make sense? Okay. Now for the underactivated case, actually the fully activated case theoretically has been studied, in the literature. Let me go back a little bit. Okay, fully activated and underactivated. How do you know that? You always know that from this matrix, the control allocation matrix. You can always find whether it's overactivated or underactivated or fully activated. The hexa-rotor that you're working with in the project, the one I showed you now, is fully activated. This is a fully activated drone. Sorry, this is a fully activated drone. This is a fully activated drone. All of these are fully activated, but also overactivated because they have more degrees of freedom than the 6 for the tilting, exactly. Okay, and the one at the top, this is the normal quadrotor and the normal hexa-rotor. They are only underactivated. Underactivated, you can find it from the control allocation matrix, and simply it means that to move in 1 degree of freedom, it has to use another degree of freedom. For example, a quadrotor, to move left or right, it has to roll, and to move forward and backward, it has to pitch. Okay.
Okay, I have a question. I understand the idea behind the tilting, but is it a function of the number of rotors we have?
No,
Is it
no.
It's 6 rotors.
It's the rank. It's related to the rank of the control allocation matrix.
We have a hexa-rotor and
Exactly, that's an excellent point. This is a normal hexa-rotor. This is a fully activated hexa-rotor. Underactivated, fully activated.
Yeah.
So it has nothing to do with the number of propellers.
In order to at least achieve fully activated accelerators, we have to at least have 6 motors.
Absolutely.
Then we'll see how to orient them.
Exactly. But you could have 3 or 4, but actively tilted, and still you get them to be fully activated.
If they're 4, you have to at least tilt 2. Is that the idea behind it?
Active tilting.
Yeah, two of the rotors at least. Yeah. Like you have to have a minimum of 6 motors
6 inputs, absolutely, yes.
for it.
Absolutely.
Because,
To at least to start thinking about whether it's fully activated or not.
Yeah.
Absolutely, yes, you're right. Yes. Okay. So that's the fully activated controller. Now for the underactivated case. So actually doing underactivated control is very hard. Okay.
for the fully activated hexa-rotor,
Yeah.
what is the maximum yaw angle for it?
You mean roll or pitch?
No, the yaw angle.
The yaw angle,
Yeah.
like this,
Yeah.
can go any angle. No maximum angle. For the roll and pitch, it depends, and I'll tell you why if you want after the lecture. Okay. Now, underactivated control is usually harder than the fully activated one. Okay. Fully activated simply is much easier because you have the range that you computed from the SE3 controller, you can always find a solution for it from the control allocation problem. But the underactivated is not the case. Now, this is a fundamental work in UAVs in general and also in control. This is actually a paper by someone called Theo Longley and more people. He's actually the first one, that actually was able to extend the SE3 controller to a quadrotor. You know how quadrotors are popular. This is actually a paper that's cited 2,000 times. Okay, and this was the simulation work that he did in this work. And actually, if you look, believe it or not, you actually have now the capacity to actually read the paper and understand it. Okay? You'll find it very similar to what we've been doing. Okay, so this is, you see, he's doing a simulation here. The drone is able to follow any trajectory. And now, a couple of years later, the guys at Vijay Kumar's group. So Vijay Kumar, actually, this is 1 year later. So this is the group of Vijay Kumar in University of Pennsylvania. Okay, very famous, has a number of TED Talks. I'm pretty sure you've watched them. Okay, and this is the work that they did implementing this controller, something similar to it, on a quadrotor. Okay.
Capable of recovering from extreme initial conditions.
This is what it means to be globally asymptotically stable, almost. Okay, you start from any initial condition, doesn't matter. You're always stable. You can go from any error to the desired error. Okay. And here they did not only stabilization. I only showed you stabilization control. We did not have any time for tracking. Extended it to the tracking is a piece of cake. If you want some references, there are many. Okay, so this actually was a paper that they have the extension to the tracking. This also the paper they have the tracking. Okay, and if you have tracking, you can make it follow any trajectory that you want. And the trajectories, you don't have any minimum angle that don't want the system to be mad at you or anything. You can go as crazy as you want. Okay, because of the fact. Provided that it's within the control inputs of the system, right? You're not exceeding the inputs. Okay, this is a very old work, by the way. So this is 2011, so 15 years ago, believe it or not. Okay, so there are much more stuff at the moment. Okay, but these 2 papers, okay, this paper has been cited 3,000 times. Okay, and this is 2000. So these are landmarks in the literature. Okay, so if you're into this field, you definitely have to read these 2. As well as This is our paper, so if you want, actually it's available online if you want the code to play around with it. And this is, yeah, if we go back, this paper also is also a landmark, okay, in fully actuated systems and tracking on SE3 in general, okay. These are the minimum 3 papers you need to read if you're into this field. I think I've been, yeah, right on time, okay. Any more questions?
For an overtreated,
Sorry?
for an overtreated system,
Yeah.
what are the other degrees of freedom apart from the 6?
It depends on how many you added. For example, let's take an example. Let me stop the lecture and then we can, if someone wants to leave, so let me answer that question offline. So let's stop here.